In the grade 11 course, we have to do a bunch of graphing of different types of functions. Parabolas are one type. We're also going to look at the square root function. We're going to look at the inverse function and a few others. And it would be pretty tough to graph each of these different types of functions using different methods. So in this course, we actually will teach you how to use a method called using an RST chart. And what RST stands for is reflections, stretches and compressions, and translations. Basically the three different types of transformations you'll see out of any function. So in order to understand an easy way to transform functions, I'm going to use an example that you would have seen in the grade 10 course of transforming a parabola. Now back in the grade 10 course, a lot of students say that they learn using something called the step pattern, or maybe even a different method. However, I'm going to teach you how to graph a parabola today using the RST chart. And once you know how to use the RST chart, you'll see that it's pretty straightforward to graph the other types of functions when we get to them. So here's our example we're going to work with today. We're going to graph the function g at x equals -2 bracket x plus 4 all squared plus 3. And we're also going to graph its parent function f at x equals x squared. Now if you aren't used to function notation yet because you haven't taken that lesson, don't worry. Just remember that anything written in function notation like this g at x here or this f at x right here can just be replaced by a y. So it's just like saying y equals x squared or y equals -2 times x plus 4 all squared plus 3. So the first step that we're going to do to graphing using an RST chart is we need to know what the different types of transformations are from from f of x to g at x. And so in this case we have 4 different transformations that are occurring. We have this plus 3 that's right here. We have this plus 4 right here. We have this 2, and we also have this negative sign that's out in front. So for a parabola, those are 4 different things that are occurring. So we're going to name what all 4 of those things are. So let's first start with the negative. We can remember that a parabola will face upwards if this number out in front is positive, but will face downwards if the number out in front is negative. So we call this, when it's a negative, it's a reflection over the x-axis. So this is a reflection over the x-axis. And it's going to be important for us to realize that it's over the x-axis, because we're going to see a bit later on in the course we might have reflections over the y-axis. But reflecting over the x-axis just turns something that's right side up and basically flips it upside down. Okay, the next thing that we have here is the 2. This 2 is adjoined to the negative, but when we talk about transformations, the 2 is actually separate from the negative. The negative represents a reflection. The 2, on the other hand, represents either a stretch or a compression. So the rule is, if the number is greater than 1, it's a stretch, and if the number is less than 1, so normally a fraction, then it's a compression. And not only is it a stretch or compression, but it's a vertical stretch or compression. It affects the y values. So here we have a vertical stretch because the number is higher than 1 of 2. You might see in your book that it will say a vertical stretch by a factor of 2, but I'm okay with you just writing vertical stretch of 2. I understand what you're trying to say. If, for example, this was half instead of 2, you would say it's a vertical compression of 1/2. Okay, let's move on to this plus 4 right here. So if you can remember back to quadratics, the number inside the brackets with the x tells us if the parabola is moving left or right. So this is actually a horizontal translation. The thing to remember though is anytime we deal with numbers beside an x value, in this case in brackets with the x, those numbers always sort of mean the backwards thought to what you think they mean. So when we see plus 4, the initial instinct if we're moving horizontally is that that means we're going to move right 4. But in fact the opposite is true. We're actually going to be moving left 4 because of this plus 4 in the brackets. So this is a horizontal translation left 4 units. And last but not least, this plus 3. So we recognize this plus 3 is the number off by itself, not attached to any of the squared or multiplying to the brackets. This tells us whether or not the parabola is moving up or down, or a vertical translation. And so this plus 3 tells us we're actually translating up 3 units. So I have a translation up 3. If you notice I'm not necessarily writing it's a vertical translation of 3, we can tell that it's a vertical translation because we're going up. Only vertical translations can go up or down, just like only horizontal translations can go left or right. So there we have it. We have our 4 different transformations, a reflection over the x-axis, given by that negative, a vertical stretch of 2, a translation left 4, and a translation up 3. So now that we know these, let's use the RST chart to help us graph what this function will look like. Step 2 in our process is to now create the RST chart. So RST again stands for reflections, stretches and compressions, and translations. But one thing we need to remember is we can't just apply these transformations to our parent function, y equals x squared, in any random order. Just like how we have to use BEDMAS when we're doing any order of operations, we have to follow BEDMAS when we do our RST chart. So reflections and stretches and compressions, both of these are affected by multiplying a number to our x values or our y values, whereas translations up and down or left and right are adding or subtracting. So it's important that we have to follow an order: reflections, then stretches, then translations. I guess it is possible to do an SRT table by doing the stretches and compressions first and then doing the reflections. But it makes more sense to me to go in alphabetical order. So R, then S, then T. So knowing that we need to go in that order, we create a chart that looks like this. We put an X and the Y values at the top, and then our order, R, S, and T, down at the bottom. And we create 6 different boxes. This will represent the reflections that will affect any X values, whereas this box will represent any reflections that affect Y values. And this one will reflect stretches and compressions, and these ones will reflect translations up, down, left, or right. So here's our function again. G at x equals negative 2x plus 4 all squared plus 3. And here are the 4 different transformations we came up with on the previous slide. A reflection over the x-axis, vertical stretch of 2, left 4, and up 3. We will now transfer these 4 transformations into our table. We'll begin with the reflection over the x-axis. Now, if you think about it, if we're reflecting over the x-axis, we're basically taking the parabola that was facing upwards and then turning it and flipping it so it faces downwards. Is that affecting the x values of the parabola or the y values? You'd be correct if you thought that this was affecting the y values. Even though we're flipping over the x-axis, it's all the y values that are changing. If we had a point that was, say, at the point 2, 4, and then we flipped it over the x-axis, we'd now be at a point 2, negative 4. So what did we do there? We basically took the y value and multiplied it by negative 1. So because that's the operation I did, I'm going to put that in the box. Multiply by negative 1. This is going to tell me that any of my y values that I have are going to need to be multiplied by negative 1 to reflect the reflection in my transformations. Okay, done. What's next? A vertical stretch by a factor of 2. So vertical is the key word here, telling me that I'm going to be dealing with y values. Vertical means up or down. So I'm stretching all of my y values by a factor of 2. basically I'm taking all my y values and doubling them, or multiplying them all by 2. So in the stretcher compression row, and under the y column, I'm taking them all and multiplying them by 2. So now we've done 2 different transformations affecting the y's. We're reflecting and we're stretching. This one's done now too. Last but not least, we have our 2 transformations, going left 4 and then going up 3. Well, let's start with left 4. Left means we're going left or right, which essentially means horizontally translating, or affecting the x values. Anything left or right affects the x values. So if I want to take an x point and move it left 4, that means I have to actually subtract 4 from what it was before. So my operation in this box is going to be to take all the x values and subtract 4 from them. Moving up 3, well, that's going to affect y values. Going up and down affects the y values. So each y value is going to need to be added 3 so that we can move everything up 3. And there you have it. We have all 4 of our different transformations now in our box. Multiplying by -1 to the y's, then multiplying all the y's by 2, and then last but not least, subtracting 4 from all the x's and then adding 3 to all the y's, in this order. Okay, so let's use this chart to now take our original parabola y equals x squared and move it to its new function g at x equals -2 bracket x plus 4 all squared plus 3. So step 3 in our process is to now map the key points to their new locations. What's important when we talk about graphing functions is that each function has a set of key points that we use from its parent function. So the y equals x squared function, or the f at x equals x squared function, has 5 key points that we're going to use. Here they are. We can remember these when we graph them back in grade 10. We have the point 0, 0, 1, 1, and 2, 4, and the point -1, 1, and the point -2, 4. You could easily get these points if you just made a table of values and subbed the points -2, -1, 0, 1, and 2 as your x values, and then just solved for what the y values would be. These are our key points, and you're going to need to memorize what these are. Each parent function that we see in this course will have their own key points, and you'll need to memorize those as well. But it'll be pretty easy once you get the hang of it. So now we use the RST chart that we created, and we take these key points and we map them to their new locations. Essentially what we're doing is we're applying all of the order of operations that we said we would be doing from the previous slide, and now using them on these 5 points. In order to show that we're mapping the new points, we just draw some arrows to show that they're going to a new location. This is the proper way of doing it, so I expect that you do this when you have to do a quiz or a test or on your exam. So each new point will be written in brackets, of course having an x value and a y value each. So we can put the commas in there. And let's just start with all of the x values. Notice how we didn't use these 2 boxes in the previous slide. In fact, for all parabolas, we never use these 2 boxes. Only the other 4 boxes are possible when we transform a parabola. So there's only one different operation that we're doing with the x's, and that's to take all of the x values and subtract 4. Well, here are our x values, -2, -1, 0, 1, and 2. So let's take each of them and do the only operation, subtracting 4. So -2 subtract 4, well, that's -6. -1 subtract 4, well, that's -5, and so on and so forth. Notice how each of these just keep going up by 1. That was pretty easy. All I did was take the x values and subtract it by 4. The tougher part is now the y values. Each y value we're going to multiply by -1, then multiply by 2, and then add 3. So when I take the number 4, multiply it by -1, I get -4. Then multiply it by 2. Well, -4 times 2 is -8. And then I want to add 3. So I go back the other direction of the number line. -8 plus 3, well, that's -5. The best part when we're working with parabolas is this 4, the y value here, that's 4. Well, we repeat the y value right down here as 4. So when this 4 gets transformed, it's also going to end up being negative 5. Oh, it's like we cut out half the work. Okay, let's do the number 1. So the y value of 1 multiplied by negative 1 ends up being negative 1. Then times 2, that gives us to negative 2. And then add 3, well, negative 2 plus 3 is positive 1. It stayed the same. I think that's just a coincidence. This 1 will also stay the same, being 1. Last but not least, this 0. 0 is really easy, because anything you multiply with 0 is still 0. So 0 times negative 1 is 0, then times 2 is still 0, and now we're just going to add 3. So we get the number 3. And now these are the 5 new points that we're going to use to graph our transformed parabola. So let's do that. Okay, so at the top we have our 5 key points, and now our 5 transform points. So step 4 is to now graph our function. And remember, we were asked to graph not only our transform function, but also the parent function as well. So let's start with the parent function. We'll use our 5 key points, and we'll graph them on our graph down here. Don't forget to label your axes. This is the x-axis, and this is the y-axis. Okay, well, let's start at 0, 0. That one's easy. The point 1, 1. And the point 2, 4. 1, 2, 3, 4. And remember, the best thing about parabolas is that they are symmetrical. So going the other way, negative 1, 1 and negative 2, 4 should look the exact same. And we can just connect the dots, remembering to extend the curve beyond our last point. And there we have it. A nice rough sketch of our base parabola, or our parent function, and we'll call this f at x equals x squared. Or you can just call it y equals x squared. It doesn't matter. They both mean the same thing. Okay, so now we're going to take our new transform points and plot them on our graph. So let me use blue, because that was the color that we used. So let's start. Notice how 0, 0 was the vertex of our base function. Well, let's look at our new vertex, negative 4, 3. So I go negative 4, 1, 2, 3, 4, and then up 3, 1, 2, 3. This is where my new vertex is going to be, right there. 1, 1 is now transformed to negative 3, 1. So 1, 2, 3, and then up 1. And then 2, 4 was transformed to negative 2, negative 5. So negative 2, 1, 2, 3, 4, 5 down. The other side, of course, is symmetrical, so I'm going to get a point here, and then a point right here. And you can verify that these are the same points that we drew up there. So draw a nice smooth curve through these points. It's kind of tricky on my tablet here. Well, that might be the best I can do. Not pretty, but I'm sure on your own paper, if you make a mistake, just use your eraser and make it a nice smooth curve through there. Now, we have to remember, over here, I've given us some reminders that we need to do. So first of all, label the axes. We did that. We're going to have to label at least 3 key points on our transform function. One of those key points should be the vertex. So let me label that one right here. The vertex here is at negative 4, 3. And then label 2 other points. So let's label this one right here. This is at negative 5, 1. And we can label this one down here, negative 6, negative 5. Excellent. Label each function. So we labeled the original function, and now this is my transform function. G at x equals negative 2 bracket x plus 4 all squared plus 3. Just fit it in there. And now label the scale if the units aren't 1. Well, each of my units were 1, so I don't need to label the scale. It's assumed that the scale is 1 unless otherwise noted. If I did go up by 2s or something for each block, I would have to write little numbers here saying, okay, I went up by 2, I went up by 4, and 6, and so on and so forth. But I didn't do that, so I'm not going to bother. Just makes it a bit more messy if I write more numbers in. Guess I should write my original functions 3 points here. So 0, 0, 1, 1, and 2, 4. Those are the easy ones. And there you have it. I've now successfully graphed my new function, transformed. Did it do what I thought it was going to do? Well, it reflected. It's now facing downwards. It's stretched. Notice how the key points are really close to each other here, but they're a bit more stretched out here. And it's also moved left 4 and up 3. It did everything we wanted it to do, and it was really easy to graph based on our 5 key points and using the RST chart. So yes, it is possible that you could have done this also by using the step pattern, but the problem is that you can't use the step pattern for anything other than graphing parabolas. The RST chart is great because you can use it to graph almost any type of other function that has reflections, stretches, compressions, and translations, which is pretty much all of the functions that we see here. And you'll also be using an RST chart into grade 12, so it's better to get used to it now and to start using it. So here are some functions that you can try. I've given you 3, and you can find some graph paper and just try them out. So for each of these, first of all, state what the transformations are, and then use the steps that I've instructed you to create an RST chart and to use it to graph. Don't forget to memorize your 5 key points, and then use the RST chart to generate your 5 new points of your transform function. Good luck!